Hello everyone, welcome to Civil Dharma. In today's session, we are going to discuss a different comparison of a beam element and a plate element. I have many queries from the students. If I model a particular beam element with the same dimension as a plate entity, will I get the same results? So the answer is yes. But yeah, you have to take care of few important points while modeling the same element as a plate entity, right? Because it is a finite element model, and in that particular case you have to discretize your members and convert it into the finer elements to get the better results. So basically what we're gonna do, so here I am considering a cantilever beam with a point load. Now this particular beam will again model as a plate entity, and then after we will check out the results whether we are getting the same results or not. So let's get started. So I am applying a point load of 20 kN on a 3 meter cantilever beam. So I'll get obviously a bending moment of 60 kN roundabout. Okay, and as I told you, I'll consider first of all a beam element with a sectional property of 3 meter length and with a 600 mm depth. Alright, and the same model will be considered or model as a plate element, and then again we will apply the same point load and we will work out whether it will give you a same results or not. Also you will get to know how you can work out the bending moment in case of the plate elements. So stay tuned with us. Now let's move on to the STAAD. Now let me just quickly show you. Here I have a cantilever beam with a fixed support its length is 3 meter. Actually it is 3048 mm, right? Now see what is the property that I have given to this particular beam. You can model it easily. Its depth is 610 mm. Right now I'm talking in the mm, and its width is 0.152 mm. So you can model it easily, right? Now the same entity I have developed here with a plate element, right? So for your understanding, I'll just quickly show you how you can model this. Okay, so first of all you have to create 4 nodes. Now see, in the Connect Edition version we don't have facility to create a plate directly, right? So you just have to first create 4 beams, and in that particular you have to go to the geometrical tab. Then you can click on the infill plate options, so the plate will be created like this. Alright, then after you can delete the periphery beams. So I have created such plate over here. Let me just quickly show you the dimensions. So basically its length is, as I mentioned, 3048 mm or 3.048 meter, and depth is 610 mm. Right, now see, I have converted this particular plate into the finer mesh. I have to discretize this plate in a finite element mesh. So basically what I'll do, I'll switch to the plate cursor first, right? In order to operate the plate you must have a plate cursor on. So I'll now select the plate. I'll go to the right click, then I'll click on generate plate mesh option. I'll choose quadrilateral meshing. Click on OK button. Now here I have 10 divisions in the depth, but in case of length I'll divide it into more finer mesh, so I'll make it 30 over here. Then I'll click on OK, right? So that's how you can create this particular element, and you have to then apply a property of plate element from here, right? 0.1524 I have applied the thickness. So you can select your plates like this and assign this to this one. So that's how you can create this particular beam element. Okay, in terms of plate, you can call it as a deep beam. So I have modeled a deep beam with a regular beam element, and with the same dimension I have created a plate element. So it's a beam entity and a plate entity with the same property, right? Now see, as it's a cantilever, we have to assign the supports over here. So in case of this plate entity, I'll select this particular nodes and assign the fixed support. So the same thing I have generated over here. So you can check out this. So now let's check out the property for a beam element. So for a beam element, I have chosen the depth as 610 mm, and in case of the width, it is 0.1524. Now in case of our plate element, it will be the thickness, right? So it is defined as 0.1524. Got it? So I hope you got this point. So the geometry is ready now. Okay, now let's move on to the loading part. So here I have generated a normal dead load case, and in that particular I have applied a 20 kilonewton point load over here. So in a case of beam, I have applied a point load over here at the end, and in case of a plate element, it is applied at the top of this node. One important thing I want to tell you over here is that when you divide your plate, it should be with a certain dimension rules, right? It should be meshed finer. Now few important tips I can give you that a plate element's aspect ratio should be as nearer to 1:1 as possible. So 1:1 means it should be nearer to a square element. Okay, aspect ratio is basically defined as the ratio of the length of the shortest side to the longest side of the element. Okay, and aspect ratio in excess of 4:1 should be avoided. Now in other words, let's say if you have a triangular plate element, that is a 3-noded plate, right? Now in that particular case, it should be shaped as nearer to as an equivalent triangle. Okay, and in case of our quadrilateral 4-noded element, it should be shaped as nearer to a square as possible. So more finer elements you provide, or if your discretization of the plate element is correct, more accurate results you can get. So currently we are checking this particular with the 30 divisions in the length part and 10 divisions in the depth part. Okay, you can go with a different divisions, right? So first let's check out how it will work. Let's go to the command option over here, provide the analysis command, and I have already added the perform analysis option over here. Then we will go to the run analysis. We have some warnings, and that is basically we have multiple structures over here, and in the other demo model we haven't provided any support specification. So we are interested in the result part, so I'll quickly take you to the post-processing mode. I'll click on the OK button. Now I'll turn off the deflection part. Now first let's check out the bending moment. So I'll click on the MZ button to check out the bending moment. So as you can see, as we have cantilever beam, we have negative moment at the top. Now let's check out what is the value. So as I told you, 60.96 kilonewton into meter, that is my bending moment. Now how you will work out the bending moment in case of the plate element. Okay, so we will understand that. Basically you can check out your plate results from here, and here you have several options available. Okay, right now what I'll do, I'll convert the forces which we get from this stress contour, and we will multiply it with the distance part in case of a plate element. Okay, so you can obtain the contour values from here. Now another important thing I want to tell you that, let me switch to the post-processing mode again. I'll turn off the deflection part. Now see, in case of the plate element, it is now meshed, and after performing analysis, in case of a nominal beam, we are getting the bending moment as 60.96 kilonewton, right? That is in this particular beam. Now let's compare it with the extracted bending moment in the plate entity model. Okay, now see, in case of plates, the bending moment at any section is the total moment developed about the neutral plane due to the longitudinal stress exerted by the infinite number of fiber sections at the said locations, right? So let me just give you a quick understanding over here. See, our plate is divided something like this, right? And here is the neutral axis. Now, as you know that in case of the beam, the upper half of the neutral axis experience the tension, right? This particular portion is experiencing the tension and the lower half experience the compression. Now these two opposite forces generates the moment due to the bending action. Now although the fiber and their corresponding stress distribution is continuous in reality, but here we need to discretize them by the finite element meshing to the account for the total force, right? So basically what I'll do, I'll get the forces at this particular corner, right? Because we have higher moment. Our bending moment diagram is something like this, if you have observed. So what we will do, we will work out the forces in this particular list of plates here. Okay, so we need to compute the summation of all the moments developed about the neutral axis. So what I'm gonna doing, that I'll work out the forces here and I'll multiply it with this particular distance from the neutral axis. So I'll get the bending moment. Okay, now let's understand how you can do this. So I'll switch to the Excel file. So for that particular here, what we're gonna do is we will work out the plate forces here, plate shear forces actually here, then I'll multiply it with the plate area and distance from the neutral axis. So in case of plate element, your moment will be your local shear force into the plate area into distance from the neutral axis. So in our case, see, this is my model. I'll show you again. So 0.610 is the depth, and as I told you, we have 10 divisions. So if I divide this with the 10 parts, right, so ultimately what I'll get the option, this is my neutral axis, right? So my each component has a depth of 0.061. So basically what I have done is 0.610 divided by 10, right? So 0.061, that will be the depth of this particular single entity. Okay, I'll show you in the 3D part so that you can have the better understanding. So I'll switch to this. See, right now I'm talking about the individual entity. So it has 0.061 depth, and this is my width, that is the plate thickness, 0.1524 that we have applied as a plate thickness, right? So each small measure part has this particular dimension, right? So here we need to work out the shear force. Then I have provided the depth, that is 612, thickness as I mentioned 0.1524, and this particular distance is from the neutral axis, right? So how you will get this particular distance? So it is simple. See, each component has a dimension of 0.061, right? So I can add this 0.061 plus 0.061 plus 0.061. So up to here you can get the distance. So the same thing I have performed over here. So distance from the center to the neutral axis will be, for this particular entity, what will be my neutral axis? This will be my neutral axis, right? I am right now talking about a small entity. So 0.061 divide by 2. So I'll get the value as 0.0305. So here I am getting at the middle depth. Okay, at the middle depth I am getting 0.0305. Now I'll add 0.061 in each entity, right? So I can get the value from the neutral axis to the upper part, and same to the bottom part, right? So this particular list is for the bottom part and this particular list is for the upper part. So I hope you are clear with the distance from the neutral axis. So NA is clear, right? Now see, I'll work out the forces from the STAAD Pro. So basically what I'll do, I'll go with the report option. First of all, we need to select the plates, right? So I'll switch to the cursor, to the plate cursor. I'll select this particular plates. Why this particular plates? Because we have a cantilever beam and we have maximum moment at the support, right? So I have selected this particular plates. Now I'll switch to the reports. Then I'll click on the plate stresses. Here I am interested in shear, local shear force. I'll click OK button. So from here you will get the forces. So I'll copy it and I'll take it to the Excel sheet over here. I have already tried it for the demonstration purpose, so now I'll paste it over here. Okay, so from all these values we are interested in this shear force value, so I'm just copying this and paste it over here. So you can see we are getting the moment exactly nearer to the same value. In the manual calculations we are getting 60. So in the beam entity we are getting the value as 60.96 kilonewton into meter, while in the plate entity I am getting the value as 60.26 kilonewton into meter. So in this way you can work out this result as well, and you can see that we are getting the similar results, right? Now another important point I want to discuss is that in your STAAD it might be a possible that your plate results are in terms of Newton per mm square. So if you wish to get your results in kilonewton per meter square, then what you can do, you can go to the view tab, click on display option, and over here from the force unit you can convert your stress in terms of kilonewton per meter square instead of Newton per mm square if your STAAD is giving you results in terms of Newton per millimeter square, or you can convert it manually as well. Okay, but if you wish your stress values in terms of kilonewton per meter square, then you can change it from here. So keep this tip in mind. So that's how you can work out your plate results. So that's how you can work out your bending moment for the plate entity. Right, so that's how you can work out this. Now one important thing I want to tell you over here, you can observe that here up to this particular nodes we have negative values. That is because in the upper zone we have tension and in the bottom part we have compression, but you can observe that the values are same, right? So in the bottom part we have compression and in the upper part we have tension. See, I have get the force value from here. Now my moment will be my force into area 0.061 into 0.1524 that I have already explained over here, right, into distance from the center to the neutral axis. So that will give me the moment. Okay, once I summarize this, I'll get the moment as 60.26. Right, now don't confuse over here with the minus sign. As I told you that the upper half of the neural axis experience the tension and the lower half experience the compression. These two opposite forces generate the moment due to the bending action. Okay, and we need to discretize them by the finite element meshing to account for the total force, and that's why we need to compute the summation of all the moments developed about the neural axis. Right, so that's how you can work out and compare your moments with the beam entity, and with the same profile we have gone with the plate entity. Right, so you can go with a more finer size with a more divisions. So provide your answers in the comment section whether you are able to get the results or not. So I hope this video helps you out understand the concepts and logic behind the calculations. So that is our basic motive. So let me just summarize again. So here what we have done, basically we have worked out the bending moment values for a beam entity as well as for the plate entity, and we got the similar results, right? But in case of plate entity, you have to take care about the modeling part, because there are certain rules that we need to follow in case of the finite element meshing. The more accurate meshing you perform, more accurate results you will get. Here we have understand how you can work out the bending moment in case of a plate element, right? So try to understand the logic and fundamentals behind the software calculation. So try to understand the logic behind the software calculations. Okay, don't just learn software, learn concepts. So I hope this video helps you out. If you like our video, share it with other engineers. Also, we have our Instagram and LinkedIn profile where we share design tips every day, so you can follow us. The links are given in the description box. You can check out our structure design courses from the website. Connect with us, learn with concepts.